Okay, so our next lesson is also concerning two connected graphs. We have one important new definition, and then we are going to find a kind of a gentle way of decomposing a two connected graph based on this new concept. So let's get started. So our new term is an ear of a graph. An ear of G is a path, so it's a subgraph of G that's a path. And the the rules are, well, I mean, if I tell you I have a path, then just as a graph on its own, you know exactly what the degrees are, right? If you look at a vertex that's that's one of the ends of the two paths, then it has degree 1 in the path, and the vertices that are interior to the path that are not one of the two ends, well, they're going to have degree 2 in the path. But I want this path, when we look at this path, we're going to be caring about the degrees of the vertices, not in this subgraph P, not in the path, but in the original graph. And the rule is that when you look at an ear, so an ear is going to be a path of our graph, and all of the interior vertices of that ear, those vertices are all going to be degree 2 in the original graph. And the ends of that path have got to be degree at least 3 in the original graph. So an ear of G is a path such that for every vertex of P, one of two things happens. Well, the degree in the original graph G of V is equal to 2 if V is an internal vertex, not one of the ends. And the degree in the original graph G of V is at least 3 if V is an end of P. So that's our definition. So that's an ear. Let me show you. Let's draw a graph. And these are not kind of deep or difficult things. I'm trying to figure out what the best way to sort of draw an interesting case here is. All this ends up feeling a bit degenerate some of the time. Okay, so there's a perfectly good graph G. Let me indicate the ears. So the ears, again, I'm looking for a path, and the rule is that all of the internal vertices of the path have got to be degree 2, not only in the path, where they're automatically degree 2, but also in the whole graph. On the other hand, the two ends of the path, oh, I should have said, it has to have a path of non-zero length. So it's a path of length at least 1. I'm looking for paths that are positive length, so non-trivial paths. And the rule again is that all the internal vertices of the path should be degree 2 in the original graph, but the two ends of the path should be degree at least 3 in the original graph. So for instance, up here, I have a very long ear that's going to be this path that I'm drawing here in orange, right? You can see that all of the internal vertices there are degree 2 in the original graph. The two ends of that path are degree at least 3 in the original graph. So that's an ear. Let me draw some others. This is an ear of length 1. That's just a single edge. Both ends of that edge have degree at least 3 in the original graph. So that's an ear. And that's always true, right? Anytime I give you an edge and both vertices have degree at least 3, then that's going to be its own ear. It's a perfectly good path. It has no internal vertices. The two end vertices have degree at least 3. So there's another ear. Similarly, here's an ear. And here's an ear. And here's an ear. Here's an ear. hope I'm not getting any of these wrong. Okay, that looks about right. So those are the ears of the graph, of this particular graph G. And that is not really kind of a deeply difficult concept. Another way of thinking about this is if you take the original graph G, you can make a new graph by so-called suppressing the degree 2 vertices. I mean, just think about sort of taking the little node and just squishing it so it goes away. If you do that, then you get down to a graph that will have no vertices of degree 2. But every edge of that new graph is actually going to correspond, not to an edge in the original necessarily, but to a path, and it's actually going to correspond to an ear, right? So all the vertices that you smushed would be degree 2. Now there's an easy observation here, is that if G is 2 connected and not a cycle, then every edge is contained in a unique ear. And I'm just going to kind of indicate the proof of that. I mean, the idea is very simple. Here's your edge. We're in a 2 connected graph. What I'm going to do is I'm going to just start from this edge. I'm going to slowly grow out a path. So I'll grow out from either end. And the rule is, if the vertex that you're ending with is degree 2, well, then I'll keep going. Then I'll add the next edge and the next vertex, right? So here's your edge E. That's where we start. I'm going to slowly grow out. As long as these vertices are degree 2, I'm just going to keep going, right? And same thing, I'll keep going on the other side too. Now, what's going to happen? I can just keep doing this until what? Well, what's going to stop me? Well, it might be that one thing that you might worry about is maybe this becomes degree 2, but the edge coming out of this doesn't form a path because it somehow loops back. But the only way it can actually do that, you see that we've actually filled up all the degree of all these other vertices. The only way it could do that is if it came back to here. And if that were to happen, then we've just got trouble. One of two things would be going wrong. Either your whole graph would have to be a cycle, and we've assumed it isn't. So if your whole graph is not going to be a cycle, then you've got a contradiction to 2 connectivity, because now when you delete this vertex, you're going to separate what's left of this green cycle from the rest of the graph, and you know there will be something more. So so in other words, this is easy. This is as easy as well, maybe hopefully I got it all right, but it's just easy to do. You start at any edge and you just grow out from either end. You keep picking up, as long as you keep seeing vertices of degree 2, you just keep growing. And assuming your graph is 2 connected and not a cycle, then you just keep growing out of either end until you stop. And that will be the unique ear containing a given edge. Right. So these ears are, anyway, this is not a really deep concept, right? We're just we're just accounting for vertices of degree 2. An ear is almost like an edge, but it's anyway, it'll pick up additional vertices of degree 2. Now, the reason that we're focused on ears is that there's a very nice theorem that is going to allow us to take a 2 connected graph G and kind of remove an ear in a sensible way to get a new 2 connected graph. So that's going to be the thing that's nice. So let me introduce our next definition. So this next definition is the concept of ear removal. So if P is an ear of G, then we remove P by what? Well, here's what we're going to do. I'm going to delete all the edges of P from my graph G. And if you do that, what is this now? What's going on? Well, if the path P was just length 1, then, well, okay, then you just got rid of the one edge and now you're gone. Now that's it. But if the path P has more than one edge to it, so if its length is larger than one, then when you erase its edges, you're going to have created some isolated vertices, right? All of the vertices that were in the interior of the path P, those will be degree 2 after you delete the edges of P. Sorry, they're degree 2 in G. When you delete the edges of P, they turn into degree 0 vertices. So they just become isolated vertices, and we want to get rid of them. So we're going to remove P by first deleting the edges of P from G. So I'm going to delete the edges of P from G, then deleting the interior vertices of P from G. Right. So again, you could do this in the other order if you want, but you do need sort of both of these because you need to handle the case where your ear is just length 1. So yeah, anyway, so let me just step up. So pick a different color. So up here, say let's focus our attention on this top ear here. So if I wanted to remove that from my graph, what would I do? I am going to delete this edge, and I'm going to delete this edge. Oh, I would have been a little bit more convenient if those vertices had both stuck around. But I'll delete those 2 edges, and then I delete that interior vertex, right? So then I'm going to delete that. That's a removal of an ear, right? So that's our general rule. Removing an ear that's a single edge is very easy. So that you just delete the edge. So if I wanted to, for instance, remove this guy, no problem. I just take that edge and I remove it. Say I've got a very long ear over here on the left. If I wanted to remove that, then I would first erase the edges, and then I'd run along deleting all of the interior vertices of that path. All right, so again, this is not really not like a deep or difficult concept here. It's like you can kind of think of an ear as almost like an edge, right? Like if you think about those degree 2 vertices, if you're willing to kind of suppress them and kind of ignore them, then ears are just the edges of that graph. And all we're really doing is deleting those edges. Anyway, so that's ear removal. Again, an ear is a special kind of path. The inner vertices of the ear are degree 2 in the original graph G. The ends of that path are not. So they're going to have degree at least 3. And to remove an ear, what we do is we delete the edges and then we delete any interior vertices. So we're the 2 ends of that, the 2 ends of that ear will remain. And right, okay, and so that's ear removal. And yeah, let me just jump ahead and get a new blank screen. So our big theorem here is the following: if G is 2 connected and G is not a cycle, then there exists an ear so that removing it leaves you with another 2 connected graph. Right. So and anytime I give you a 2 connected graph, there's always going to be some ear of that graph so that when you rip it out, you are left with a new 2 connected graph. Oh, sorry, 2 connected graph that's not a cycle. So wait, this bottoms out at cycle. But if I give you a 2 connected graph that's not just a cycle, then you can always find an ear so that when you remove that ear, you leave a 2 connected graph. Now, I hope this actually instantly springs to mind the idea of using this as a tool for proving things inductively. Right? You saw back when we learned about trees, anytime I give you a tree as long as it's got at least 2 vertices, it's going to have a leaf. Oh, actually, at least 2 leaves, but it will have a leaf vertex. And if you delete that leaf vertex, you have a smaller tree. And that's a super powerful tool for proving theorems by induction about trees. Here we've got a similar sounding statement. In the land of 2 connected graphs, we have an operation that will take a 2 connected graph and give us a slightly smaller 2 connected graph. We take an ear and we remove it. If you do that, you're going to be left with a smaller 2 connected graph. If you are trying to prove something by mathematical induction about 2 connected graphs, this is a fantastic looking tool, right? You take one ear, you remove it, you've got a 2 connected graph. You can now apply your theorem and see what it gets you and try to put that ear back. So I'm not trying to actually use this right now. I'm just advertising it as a tool, and this is like a thing that we love, right? You have a class of graphs you want to prove something for. If you have an operation that takes something in that class and gives you a smaller thing in the same class, you can really be off to the races with some of these inductive proofs. Right. So let me draw a graph and talk about removing some ears. Okay, so here's a perfectly good graph G. This is in fact a 2 connected graph, as you can pretty readily verify. So again, each edge is going to be a unique ear. Some of these ears, if you remove them, you will be left with a new 2 connected graph. In some cases, not. So let's see an example. So for instance, I have an ear here in red. If you remove that ear, you will no longer have a 2 connected graph. Here's another ear that you better not remove if you're hoping to stay 2 connected. Here's another ear. If you remove that ear, you can see that you will have a 1 separation down here. So we don't want that. So you better not remove that ear. And similarly, you can't remove that ear, or you will be left with a graph that is no longer 2 connected. However, there are lots of ears that you can remove in this graph. If you remove this ear, you will still have a 2 connected graph. If you remove this ear, you will have a 2 connected graph. Or this one, or this one, or this one, this one, this one. Oh no, sorry, that last one I wrote wasn't valid. I can remove, yeah, I'm safe removing this one. I've got an ear right here that's bad. This ear is also okay, but there's a bad one right here. That single edge ear, if you remove it, then you can see will create a cut vertex. So if you remove it, you will have a graph that is no longer 2 connected. Right? So what's happening here again is that I've given you a graph that's 2 connected, and it's not a cycle. That means every edge is in a unique ear. Again, easy to find. You just start with the edge and sort of keep pushing out on either side until you get to a vertex that's not degree 2, and that's where you stop. So when you're done pushing, all the internal vertices will be degree 2, and the ends will be degree at least 3. Now, what we're interested in doing in this theorem here is showing that you're always guaranteed the presence of an ear whose removal leaves you 2 connected, so long as the input graph is 2 connected and not just a cycle. And anyway, so here I'm showing you a graph G, and there are some red paths that there are some red ears and green ears. And the red ears, if you remove them, you will be left with a graph that is not 2 connected. The green ears, if you remove them, you will be left with a graph that is 2 connected. And so our theorem sort of says in this red-green context, our theorem is telling us that, in fact, every 2 connected graph always has at least one green ear, at least one ear that you can remove, so that the resulting graph is 2 connected. Right. Maybe I'll say another word about this process. So, I mean, in fact, I made a modification to the notes this time around. So I sort of felt like I just wanted to say some of these things a little bit differently. This is usually cast in the context of a decomposition. And what that means is we imagine starting with our two connected graph G, and we imagine repeatedly kind of grabbing an ear and, it sounds very violent. We take an ear and remove it from the graph, and another ear of that new graph and remove it, and kind of repeated that operation. So we can, by repeatedly applying this theorem, start with the two connected graph and repeatedly take off one ear at a time and move down until we get down to a cycle. Right? This is going to bottom out when our graph becomes a cycle. And so now you can think about this, this kind of iterative process a couple different ways. You can think about taking your original graph G and applying this theorem, removing an ear, applying this theorem, removing an ear, so you get a sequence of ear removals that bring you down to a cycle. You can also kind of turn this around and say, well, if I have you a two connected graph and you want to construct it, you can imagine starting with a cycle and kind of repeatedly doing the reverse of removing an ear. You kind of add back an ear, and you can do that to grow up to any two connected graph. So anyway, that's the sort of classic way that this is generally described, but I'm writing it in this form, in this sort of simpler form here, where I'm just talking about finding one ear. And the reason I'm doing that is that this is usually the theorem that you want to apply when you want to go and you do something by induction. When you want to prove something by induction about two connected graphs using ear decomposition, usually you don't have to reduce it all the way to nothing. Usually you're just doing one step. So the theorem I'm describing here is a single step of the reduction. Okay. Anyway, so this is our theorem on ears. And let me go ahead and get going with the proof. So here's the here's the idea. I'm going to start with my graph G. What do I know? I know it's two connected and not a cycle. Well, what I'm going to be doing is I'm going to be choosing a subgraph so that that subgraph itself is two connected and not the whole graph. And in fact, I'm going to choose a maximal subgraph. So I'm choosing a maximal subgraph subject to two constraints. So the first constraint is that H has to be two connected. The second, what am I writing? The second is that H is not the whole graph. Right? So again, I have this big two connected graph G. I'm going to be choosing within it a maximal subgraph H, subject to the constraints that 1, H has got to be on its own just a two connected graph, and 2, H cannot be the whole of the graph G. Of course, if you didn't add the second restriction, the maximal subgraph would just come back being G, and I don't want that. I want something that's sort of just a teeny bit smaller than G. And in fact, what we're going to show is that this subgraph H that we found, it's the graph that you get from G by doing a single ear removal. And that's going to be the proof of our theorem, right? I'm trying to show that you can remove some ear to get a two connected graph, and this H that we're choosing here, that is the two connected graph that you're going to get. So anyway, but for starters, we're just choosing H. I'm choosing a maximal subgraph H that is two connected and not the whole graph. How do we know that such an H even exists? I mean, there's a danger. You can always say words, but if I'm actually going to choose something, there had better be at least one thing there to choose. How do I know that there's any subgraph of G that's two connected and not the whole graph? Well, the answer there comes from the presence of a cycle, right? We know that because G is a two connected graph, if I give you any two vertices of the graph G, there will be a cycle containing them. That cannot be the whole graph, right? By assumption, our graph G is not a cycle in and of itself. So a cycle is going to be a two connected graph. A cycle contained in G is a two connected graph that is not the whole graph. And that means there's at least one subgraph H of G satisfying properties 1 and 2, and therefore it's perfectly valid to choose a maximal one. Right? So that's where we are. So we've now, we know that there are subgraphs satisfying these two properties. We have chosen a maximal one, and now we're going to show that in fact this graph H, it's super close to G. In fact, H is the graph you get from G by removing just a single ear. And how are we going to do that? So here's the thing we'll employ. I know that H is not the original graph G. And so H is not empty and not everything. And that means that there's some edge that's in H and some edge that's not in H. And I'm just going to choose two of them. And I'll get my notes. I'll use the same letters as I did in the notes. Again, H is not an empty subgraph. It's a two-connected subgraph. It's got at least 3 vertices. So it's got to contain an edge E. It's not the whole graph. You can't contain all of the edges in the graph, so there's some edge F that's not. Now, my original graph G is 2-connected, so I know if you give me any 2 edges in G, there's a cycle containing both of them. So let's choose a cycle C, a subgraph of the original graph G. I'm not in H, I'm in the original graph G, such that both E and F are edges of my cycle C. I wonder to what extent I can kind of draw a picture here. Okay, let's say this is H. This will be the big graph G. I'm not exactly sure what I'm doing here, but here's an edge E that's in H, and an edge F that's not. Of course, I said F is an edge not in G. It's possible that one or both of the ends of F are vertices of the subgraph H. Sorry. Again, by assumption, F is not an edge of the subgraph H, but it is possible that one or both ends of F are in H. So be it. But now what I can choose is now I've chosen a cycle that contains both E and F, and I'm just going to draw something that's possibly a little deceptive here. Maybe that's the cycle C. So the cycle C might sort of weave in and out of our subgraph H. Right. Now, here's what we're going to do, and I'm going to sort of describe this first just a little bit with the help of a picture here and drawing some squiggles. So I've got this cycle C. It contains my edge F. What I'm going to do is I'm going to start from the edge F, and I'm going to start moving out from either side. And I'm just going to stop as soon as I get to a vertex of H. Okay? So again, I'm going to start with this edge F, and I'm going to sort of move out this way, and I'm going to stop here. Maybe this is the first vertex of, maybe not. Let me add some red vertices just for, I don't know, in the hopes of being clear. Okay, so there I've got my cycle C. Now what we're going to do is I'm going to walk out from F, and I'm going to keep going until I get to a vertex that is in H. And then I'm going to do that on the other side as well. I'm going to keep walking out until I get to a vertex of H. So in other words, I'm going to take P to be a path that's contained in the cycle C and contains my edge F, and I'm going to insist that I'm going to insist that all of the internal vertices of P are not in H. So what's happening here? I'm drawing you a purple path P. Okay, and what's happening here is P is it's going to be a subgraph of our cycle C. It's a path, and it's going to be a maximal path containing F, with the feature that all of the interior vertices of P no interior vertex of P lies in H, such that no interior vertex of P is in V of H. Right, so again, I mean, we're choosing a maximal path, but it just means we're going to just keep growing. Like P will start with P. You can think of starting with P just being the single edge F. If both ends of F are already in the subgraph H, then fine, you stop. If this end of F is not in the subgraph H, then you're just going to keep going. You're going to keep walking out along this cycle, and at some point you have to hit a vertex of H, right? Over here, I don't know, maybe I'll just sort of bold it in a little bit. Over here, on the other side of this cycle is the edge E. The edge E has both ends in H, right? Both of the ends of that edge E must lie in H, because the edge E itself lies in the subgraph H. So both of those end vertices lie in H. So what that means is if I start over here at F and start kind of growing out, well, I'll keep walking out until I get to a vertex that is in H, and if I do that on either end, I'm going to be left with this path P. Now, here's the key thing. So what does this path P look like? Well, the path P, it's looking like an ear, right? So the path P, when you add it to H, it's going to be an ear. And in fact, the key feature for us really, though, is that H union P, that subgraph H union P, is going to be two connected. And that's the key feature. Now, I call that H prime. So I'm going to consider, basically, I'm trying to argue here that that this graph H is just one ear away from the graph G. So what I'm going to do here is I'm going to construct a graph that's bigger than H. Here it is. It's H prime. It's H union that path P. And my claim here is that H prime is two connected. So I'm claiming this is a two connected graph. Now it's easy to see that this graph is connected. Of course, I better just do some space up here. So the subgraph H is a connected graph, and the path P is a connected graph, and I have two connected graphs sharing a vertex. So I have two connected subgraphs of a graph G, and those connected subgraphs share a vertex. Then we know that their union is connected. So it's certainly the case that H union P is connected. But moreover, those two H and P, I know exactly what their structure is. Suppose you take H union P and you delete, so the subgraph H prime, suppose you were to delete from that a vertex that was a vertex of H. Well, then what's left of H is going to be connected. Maybe you deleted an end of the path. You couldn't have deleted an internal vertex of the path because you deleted a vertex of H. But maybe you deleted an end of that path. But in any case, what's left of the path is connected. So again, I'm in a case where I have, H delete that vertex V and P delete that vertex V are connected subgraphs that overlap on a vertex, so their union is connected. So in other words, if you took this graph H prime and were to delete from it any vertex that's a vertex of H, then you would be left with a connected graph. Similarly, if you were to delete a vertex that's not in H, so that would have to be an internal vertex of the path, well, then your path would break into two parts, but no problem. After you delete that vertex you've deleted, your path is now broken into two parts, but both of those two parts intersect with the subgraph H, and H is connected, and so when I take the union of all those things, you get a connected graph. So in other words, I'm maybe saying that a little quicker than I should. If I have said that a little bit too quickly, I want to encourage you to just go back and think about it. But in short, the claim is that H prime, which is H union P, is two connected. So what's going on here? Well, somehow this looks almost like it's going to contradict our basic assumptions, right? H prime is two connected, so it satisfies property 1, and it's bigger than H. So why does this not contradict our choice? It can only be that H prime is the whole graph G, right? The only way that this subgraph H prime that we've just constructed does not contradict our choice of H, right? We just made a bigger two-connected subgraph. So it's contradicting our choice of H unless this is the whole graph. So by our choice of H, we must have H prime equal G. So in fact, H prime is the whole of the graph G. But now what's happened here is that, well, we can see that the graph H is what you get from G by removing the ear P. So P is an ear of G, removing it yields H, and that completes the proof. So we've now shown that there's a path P, there's an ear P, and when you remove that ear, you're going to be left with a two-connected graph, namely in this case H. So as I said, this is a really nice theorem for proving things about two-connected graphs. If we have a two-connected graph and it's not a cycle, then you're guaranteed the presence of an ear, and when you remove that ear, you will be left with a smaller two-connected graph. And I will stop the lesson there.